Jupiter's magnetic field is the strongest of any planet in the Solar System. With a dipole moment of 4,170 Gauss, 4,170 mt, that is tilted at an angle of 10.31 degrees to the pole of rotation. The surface magnetic field strength varies from 2 Gauss, 20 mt, up to 20 Gauss, 20 mt. This field is thought to be generated by eddy currents, swirling movements of conducting materials, within the liquid, metallic hydrogen core. At about 75 Jupiter radii from the planet, the interaction of the magnetosphere with the solar wind generates a bow shock. Surrounding Jupiter's magnetosphere is a magnetopause, located at the inner edge of a magnetosheath, a region between it and the bow shock. The solar wind interacts with these regions, elongating the magnetosphere on Jupiter's lee side and extending it outward until it nearly reaches the orbit of Saturn. The 4 largest moons of Jupiter all orbit within the magnetosphere, which protects them from the solar wind. U-200A69, U-200A. The volcanoes on the moon Io emit large amounts of sulfur dioxide, forming a gas torus along its orbit. The gas is ionized in Jupiter's magnetosphere, producing sulfur and oxygen ions. They, together with hydrogen ions originating from the atmosphere of Jupiter, form a plasma sheet in Jupiter's equatorial plane. The plasma in the sheet co-rotates with the planet, causing deformation of the dipole magnetic field into that of a magneto disk. Electrons within the plasma sheet generate a strong radio signature, with short, superimposed bursts in the range of 0.6 to 30 MHz that are detectable from Earth with consumer-grade shortwave radio receivers. As Io moves through this torus, the interaction generates Alpha waves that carry ionized matter into the polar regions of Jupiter. As a result, radio waves are generated through a cyclotron maser mechanism, and the energy is transmitted out along a cone-shaped surface. When Earth intersects this cone, the radio emissions from Jupiter can exceed the radio output of the Sun.